Hi everyone, my name is Antonia Alomar, and today I will present you the idea behind my research project. Let's start trying to analyze some images. If I ask you to identify what babies have abnormal face characteristics, do you think you will be able to do it? Probably, the vast majority of you could identify that the first image corresponds to a baby with Down syndrome, and also could see some abnormal face characteristics in the second image. However, actually, all of the babies of this slide have a genetic syndrome, and in consequence, have some affections in the cognition and the development. Even for expert clinicians, some of these symptoms are difficult to identify, as some of the patterns are really subtle and there exist thousands of genetic syndromes with different symptoms and phenotypes. Moreover, some of them are really rare, which makes experience really important. In consequence, an accurate diagnosis can take up to 10 years or more, because a long list of tests and specialist examination are required. But why not just perform a genetic test on everyone? Well, that would be actually really expensive and not useful at all, as still a lot of syndromes have an unknown cause. So our aim is to help clinicians in the detection of abnormal faces with underlying condition in early stages of life. We propose performing a face-based genetic screening using 3D ultrasound and 2D images. The idea is to develop a multimodal neural network that reconstructs the 3D facial morphology and analyzes if it exists or not an abnormality. This analysis presents several challenges and limitations, such as data availability and quality, because we cannot control either the movements or the expression of the babies or the low resolution and noise of the 3D ultrasound volumes. To overcome some of the challenges, we constructed the DTIC to help us to reconstruct the 3D shape with more detail and more quality than the 3D ultrasound and the 2D images. It is a 3D morphology model that has the particularity of letting us control the identity and expression, which is useful when reconstructing faces from multiple views, as the expression can change. The ultrasound fitting fits the morphology model to the closest face that represents the information available in the 3D ultrasound. Whereas for the postnatal reconstruction, we create a novel deep learning architecture that takes as input the frontal, the left, and the right pose through the 2D transformer encoder, and then the concatenated encoded images are fed into the multinet that integrate the embedded spaces into the space of the 3D graph convolutional face morphology model that will decode the 3D face that satisfies the information seen in the multiple images taken as input. This step would be detecting anomalies in the 3D reconstructions to help the clinician. The take-home message is that we try to perform early diagnosis of craneofacial anomalies via facial genetic screening to help developing the correct treatment or therapy. Thanks for your attention.